So welcome back. Our second speaker of the day, also from Potsdam, is Sven Raum. I hope I spelled his name correctly. And he will talk about stable rank 1 for group C-star algebras.
Okay, thank you very much. Thanks for the invitation. Thanks for making the visit possible, despite the fact that we cannot spend money from Potsdam at the moment. That was very nice. We got this grant together, so I hope that we will be around frequently the coming 2 years. And I like the atmosphere. It was the first time that I'm actually in the institute this time. So yeah. Okay, I wanted to talk about stable rank for group C-star algebras. Feel free to interrupt me at any moment when you feel like I didn't define what I'm talking about. Okay, I will tell you what stable rank 1 is, and I will briefly recap group C-star algebra, assuming that you probably know this, but it's maybe not bad to anyway tell you again. So the key structural notion will be stable rank 1. So stable rank 1 for group C-star algebras. And we should first agree what stable rank 1 means. Stable rank 1 is, of course, one of several items. There's stable rank n for any n, but stable rank 1 is particularly useful and particularly easy to define. Notably, if I have a C-star algebra, has stable rank 1, if the invertibles in its unitization is dense, are dense. What is our dense? This subset is dense. So the invertibles are dense. So I pass to a unitization just to make sure that I can reasonably talk about invertibles. Forget about it if your C-star algebra has already a unit. And there are plenty of those. There are so many that given any element in my algebra, I can approximate it by invertibles in there. And as a matter of fact, if A is already unital, indeed, I can suppress the unitization in this definition, but this is the one way that works. I will tell you a little bit about where stable rank 1 came from in a second, but first I want to put this into a context of dimensions. This is one of several attempts to get a notion of dimension bounds for C-star algebras. And for topological spaces, there's, at least in separable metrizable spaces, there's, I guess, one uniform concept of dimension that you could apply. And whenever you come up with a reasonable definition, it will match the covering dimension, right? And then you can compare this on abelian C-star algebras this way. Let's say X locally compact Hausdorff space. Then you have C0 of X as a C-star algebra. And I would abbreviate this as SR1, stable rank 1, so that I don't need to write it out every time. This holds if and only if the dimension of X in this notion, or in this sense, is less or equal than 1. So it's a way to make sure that your C-star algebra has low dimension. And the picture you should have in mind is that you can take a continuous function, let's say defined on a circle, and it should take values in the complex numbers. Now, the reason why it could possibly not be invertible as an element of the continuous functions on S1 is that it takes somewhere the value 0. And since you have dimension 1 for the circle, you can perturb your function a tiny bit, so moving it away from 0, and it will be invertible, the resulting function. And you can do this for arbitrary functions like this. And the same argument works whenever your space has a dimension at most 1, and it works precisely. Okay, so this was historically one attempt to do these dimension things, but it had it had some other motivations from K-theory that I'll explain in a second. But there's another source of examples that one should mention as C-star algebraized, and that's things coming from classification. And here I will use terms that maybe not everybody who knows classification will know as being defined, being definable, but these are key notions in the classification program. So there's this mysterious algebra Chang-2, the set. Chang-2 algebras are usually used to define set stable. So you're supposed to be stable under tensoring with this algebra, meaning stable as in isomorphic to the original algebra you had. And if you have, sorry, let me make a sentence like this. Every set stable, what? The sentence does not make sense. Every, one should proofread one's notes, but anyway, every simple set stable unital and finite C-star algebra has stable rank 1. So simple as in no non-trivial ideas. You probably know this unital is this. Finiteness is one requirement for C-star algebras that you easily can witness by having some faithful trace. That's the way to check it. So if you have a functional that is traceable and faithful on your C-star algebra, this will ensure finiteness. And the set stable is this mysterious regularity condition that is often not easy to check, but has been checked quite often now by people working in the classification program. And whenever you're in this situation, then you will be stable rank. I have stable rank 1. And it is a fact that there are many C-star algebras which satisfy all the other attributes, but set stability and still are stable rank 1. And this has been one reason why people already in the, I guess, early 2000s, end of the 90s, started to get interested in this notion also from a structure of C-star algebra point of view, not only from K-theory point of view.
Even without the unital.
I'm not an expert in the classification thing, and I couldn't find the reference for non-unital, but this might be very. Okay, Washington did this. Okay, yeah, this. Wait, it's not essential. I mean, this is to say, like, this is a notion that came also from this idea or circle of ideas of classification, and it's more flexible than set stability in the suitable framework. What I should also say is, like, there are abstractions. You could probably criticize unital. Okay, yeah. Simple, probably not so much. This is God-given in the classification program, but finiteness is not. But for stable rank 1, it will follow. So if you want to have this conclusion, finiteness should be assumed. So every C-star algebra with stable rank 1 is finite in the sense, not finite as in a finite set, obviously, but finite in the sense of operator algebras. And the reason is that if you have an infinite element witnessed by some actual isometry, which is not unitary, the index of this element in K-theory will be an obstruction to being approximable by invertibles. So you could use some basic K-theoretic arguments to show it cannot be stable rank 1 in this case. Okay, and this closes the circle to K-theory, and that has been one of the original motivations to actually introduce stable rank 1. I mean, operator algebras were not the first ones to come up with this one, but motivation for stable rank 1. So what Riefel at the time, Riefel showed that the map from the unitaries of the unitization. Let's take A to be a C-star algebra. Then we can take the unitization and take unitary elements in there. All those elements will definitively define me elements in K1 of the C-star algebra, because K1 is built out of unitaries after matrix amplifications. There's an obvious kernel to this map, and these are all those unitaries that can be connected by a path of unitaries to the identity, to the trivial, to 1 in the C-star algebra here. And if your C-star algebra has stable rank 1, we will prove that this is an isomorphism. So that is if A has stable rank 1. And this is in line with what people had done before. This is in line with the stable range plus stable range, it was called actually in algebraic K theory, where people in the 70s were wondering how to compute algebraic K theory, although there was not yet a very, completely functional definition of K theory at the time. But Bas came up with a much more complicated notion of stable range that could provide you identifications of algebraic K theory. And Riefel, in the search for a good way to understand this type of things, introduced this notion of stable rank, because it seems like this is a thing that could be easier, but that's actually not true. This is more difficult. This is the one that can be easier computed because you have homological algebra methods, and then he could understand non-stable K theory. This is the keyword by which this site goes. Okay, so this is why people were originally interested in stable rank 1. And since then, I think it has developed quite a bit to tool in the structure theory of C-star algebras. Did I give nice keywords? Yeah, okay, I didn't write much for this in the notes. Like nowadays, one could, stable rank 1 is a key ingredient. In structural results. For C-star algebras via a specific tool, via the Kunst-Semi group. So there's an invariant that is much finer than K theory and called the Kunst-Semi group. And it turns out that stable rank 1 lets you prove specific order properties. It's an ordered abelian semigroup. And it lets you prove certain order properties for that semigroup, which then help you to solve structural problems for C-star algebra. So there's a detour, and the stable rank 1 has turned out to be the key ingredient. So then I take this as an input, and I'm a person specialized more in operator algebras and groups, and I want to understand which groups have C-star algebras with stable rank 1.
What were the properties that you get from stable rank 1?
I'm not the expert, but there's this, how is this middle property called? You have this type of interpolation problem. This, and then you get a set in the middle and a reach interpolation. Thanks, yes. This type of thing, if I remember correctly, this was one of the properties, but there are more. Hannes is definitely, Hannes Thiel is the expert to ask for order properties in Kunst-Semi groups in relation to stable rank 1. This type of things, if I remember correctly, are what they prove, and then can use it in a clever way to solve all type of problems in actual C-star algebras. Right. Yeah. Other questions at the moment? No? Okay. So then I'm not an amenable person, at least not in operator algebras. Then what should I say? Like, let's say non-amendable C-star algebras with stable rank 1. And what I want to do is like, I will tell you a little bit about examples, what is known, and what we would like to know, so open problems. So the earliest example of a non-amendable C-star algebra which has stable rank 1 came, I guess, from the reduced group C-star algebra of F2. Recall for a group gamma, we have the reduced group C-star algebra. This is the closure of C gamma represented by a convolution on L2 of gamma. So you can take an element in the group ring. It will act on L2 just by a standard convolution formula where you linearize the usual translation action on the left. And it turns out that this is action by bounded operators. So you end up here in the bounded operators on L2 of gamma, and you close up in the operator norm. That's the quickest way to introduce C-star reduced. Okay, it's one of the C-star algebras we are interested in because it links very much to representation theory. I guess my favorite way to convince somebody who's not working directly in operator algebras and finds this interesting anyway is one result of Boutonnet and Udaye, which shows that there's basically a dichotomy. So I just do this spontaneously because I realize there are people who do not have an operator algebra background, and I think it's good to tell you in particular why these objects would be so crucial. The point is the following. This is a result by Boutonnet, Udaye, and I must admit that I don't remember the year 2001. I think 2001 question mark, roughly around this time. And what they prove is that for specific groups, let me take as an example SL3Z. If this is a unitary representation, to rep without a finite dimensional non-zero subrepresentation. Okay, so I exclude just finite dimensional subrepresentations. Then the completion that I would get inside this representation, I can map this group there and generate a C-star algebra. Then this maps onto this reduced group C-star algebra. So if I want to understand unitary representation theory of groups that we all like, linear groups, in particular SL3Z now, I mean, there are some requirements there, of course. Then we have a dichotomy. We can, on the one hand, understand finite dimensional representations, and there, via like properties of these finite dimensional representations and concurrent subgroup problems, we will in the end do representation theory of finite groups of Lie type. And on the other end, we will in the end do C-star reduced. Okay, so that shows you that this is probably a difficult to understand object, but also interesting. Okay, for which groups this holds? Irreducible lattices in higher rank groups, Lie groups. I mean, you can do it also over algebra, algebraic groups, but let's stay with real points. I mean, like, let's say higher rank lattices in just real algebraic groups. for the rest, I would have. I mean, the point is, for the other parts, I should look things up, the precise results, because there are sometimes caveats. Yeah. Okay. Okay, it's not as we said that I will work with. As far as I know, stable rank 1 is open for this one. But C-star reduced F2, that was one of the first examples, or the first example of a non-amenable C-star algebra for which stable rank 1 was known. So this is a theorem of Dykema, Horgrup, and Rödam from 1997. And they showed that C-star reduced of F2, let's say, and more generally, group C-star algebras of free product of groups have stable rank 1. So this was the first results in this direction, and basically established the techniques. I will tell you, time permitting, a little bit about the techniques. But let me tell you the story further. Like, people looked at the methods in there and could get things a little bit more abstractly working. This was a result of Dykema de la Harpe. That was, I certainly did a mistake here. This cannot be, this is wrong. Probably it was 2003. Let me not write any number then. If gamma is a torsion-free hyperbolic group, e.g. a surface group, e.g. a surface group in genus at least 2, in genus 2, then the reduced group C-star algebra has stable rank 1. Okay, so hyperbolic groups, as in Kromov's hyperbolic groups, which are torsion-free. Okay. Fundamental groups of closed surfaces simply, I mean, you can take them punctured also if you like. I mean, depending on the genus and the number of punctures, they are hyperbolic or not. And the easiest way to ensure that they are hyperbolic is that you just take genus at least 2. So at least 2 of these holes. Yep. And you're allowed in principle to put punctures additionally, and then lower genera also help work. It's a combinatorial problem. I'll tell you in the method of proof where this can happen, but it's not obvious from the statement alone. A priori, torsion is not a problem for stable rank 1, not conceptually, but it's an obstruction in the method of proof. I mean, they had the free products of C-star algebras as long as they satisfy the so-called Avitsur condition, which is about the existence of 2 unitaries, one in each, well, 2 unitaries in one factor of the free product, another unitary in the other one, so that you have certain conditions on the traces. All unitaries should be trace-free, and the product of one times the adjoint of the other in the first factor should be also trace-free, so that you have enough freeness to basically pretend your free product looks a little bit like Z mod 3, free product Z mod 2, the PSL2 set case. They use I mean, in the end, it looks a lot like making the free group result work in a more general setup. Yeah, that's so they have other. I just give these as examples in the setup of group C algebras because then I have a uniform framework to state things. So another theorem is the Mover-Osin. Oh, that was much later, 2020. As far as I understood, result in principle was known for a few years to them, and then they wrote it down in this. So maybe for 2-3 years it was already known, but still there's quite a big gap to the results before. That has some technical reasons. It was technically much more involved than this. If gamma is acylindrically hyperbolic with no non-trivial finite normal subgroup, such as one example that would fall in here and not in the ones before, such as triangle groups. Then C star reduced gamma has stable rank 1. So let me draw a picture to tell you what a triangle group is in case you have not seen it before. You take the hyperbolic plane and a triangle in there that defines your 3 geodesics, and you define the you consider the reflection group generated by these reflections. That's a triangle group, and if you do it in the hyperbolic plane, then you get a hyperbolic group. The point is that I write acylindrically hyperbolic to also account for the fact they really prove things far beyond hyperbolic groups only. But in the setup of hyperbolic groups, in the beginning, torsion was the problem, and these have obviously torsion because you have order 2 elements coming from the reflections. They were not covered by things before. Even these type of very simple examples were not covered. Okay, so but there's still an obstruction, and this is the existence of finite normal subgroups. So that was open, and this I could fix last year. So gamma is acylindrically hyperbolic. No assumption further. And let's take the easiest example that is in this class, but not in this one. DL2Z has obviously the center as a normal subgroup and is not covered by this, which is unfortunate. You can do mapping class groups of punctured surfaces of arbitrary type if you like, but let me not mention that, such as when as C star algebra of gamma has a stable rank 1. Okay, so now we know it in the generality we would like to for acylindrically hyperbolic groups. And to not make any wrong impression, I mean, the main work is really in this result. This just looks at how you can basically update a few things at the crucial steps that they didn't maybe see as such and get this result. But now we have the results in a generality that we like. Still, as I mentioned before, there are plenty of interesting groups out there for which we do not know whether their C star algebras have stable rank 1 or not. Okay, what I would like to do, if you do not have any questions at this moment, is give you a blueprint for a proof. Because interestingly, for non-amenable C star algebras, I know of exactly one proof strategy that people can implement at the moment, and all proofs that are in the literature are in one way or another variations of that strategy. And that strategy came, unsurprisingly, from Dijkema, Hagerup, Rödem, and people over the years found out how to deform and adapt it to the different situations. Okay? So then, no questions, and I continue this way. And which one did you use, Karen? Where the Oh, I think you used the sponge in the, okay, combined work. Okay. Okay. So the proof strategy, blueprints for proving stable rank one. So I will do it with the example of groups, and I will tell you why F2 in particular would satisfy certain properties. There are two ingredients that we need. Two ingredients. One is it looks very much like a combinatorial input, and I think this is how a priori we should think about it, but in practice you verify it by some dynamical properties or geometric properties, if you will. So for a finite subset S, there's T in gamma such that S times G in gamma generates a free sub semigroup. So that means whenever I take elements from this, the tuple from there, then I get, of course, the group element in gamma by multiplying these, and that group element will recover my tuple uniquely. Okay, that's a statement of generating a free sub-semigroup. That's a very combinatorial property. The second one is like geometric harmonic analysis flavor. So this is what is called the rapid decay property. So a group with some length function, and I just now implicitly fix a length function coming from a word metric. So let me say gamma is finitely generated, and we get the associated word metric, and we consider the associated word, well, probably I should say word length, not metric in this case. Then I can make the following, I can make the following statement and require a group to satisfy it. It satisfies RD if there is a polynomial f, let's say, monivariate, such that for any A in the group ring, gamma, with its support of A in the, let's say, R ball around E. So this is a finite linear combination of group elements, and they require that these group elements all be in the R ball around E. So they may not have length exceeding R. If this is given, then I want to require that the following estimate holds, such that for we have that the absolutely mysterious operator norm in C star reduced is bounded by something that a high school student can compute, the 2 norm times this polynomial. Okay? That's the rapid decay property. It's very useful if you want to study the left-hand side, because it's extremely hard to calculate norms of elements that are concretely given to you. But this side we can actually control. The R appears here as in the radius. So the support of A is contained in the R ball. So you cannot expect a uniform estimate because it will simply not be true that the operator norm in general will be bounded by the 2 norm. No, sorry, the polynomial f is given, and it appears here in f of r. I mean, this is my very bad handwriting, sorry. I just evaluate the polynomial f in r. So there's a polynomial multiplicative mistake when you do this. The 2 norm s in L2 of gamma, so summing the squares of the coefficients and taking the root of that sum. Yeah. So, right, so really this side is the easy one, and this one is the difficult one in principle. Now you can put these things together. Let me see whether I have the time to put this together. Yeah, in 5 minutes I can do this. I guess 5 minutes is fine for the time. I don't know. I mean, since I started a little bit later, I'm fine to stop at any. Okay, then try to describe to you how to put these things together. So these are the ingredients. So now, sketch of proof of stable rank 1. So there is this ingredient that if, let's say, A, I call this C star reduced of gamma, had not a stable rank 1, there is a structural result that tells us that this is violated in an extreme way. Then there's an element A in A such that the norm is 1, and at the same time the distance to the invertibles is also 1. Okay, this is one result. Radam proved this at some point. Okay. Now let's take this element and get a contradiction. Okay. How can we do this? So let's look at our ingredients. The L2 norm appears. So let me do this connection first. What do I know about something with L2 here? Well, since I is not a unitary, I mean, it's not it's a distance 1 to the invertible, so it definitely cannot be invertible and certainly not a unitary, right? But this means this is a positive element that is strictly less than 1. And thus, the norm of A in the 2 norm there, and this is the standard trace that Sanas introduced, the canonical trace, she called it, evaluated at this, and this is strictly less than 1. Right? So this is something that we know just completely abstractly from this input data that it must be strictly less than 1. At the same time, let's reformulate this one to something that will be equal to 1, and then deduce that 1 is less than 1, which will be the desired contradiction. We have this one. Note also that the spectrum of A is the unit disk, because the spectrum is all those lambda in the complex plane such that A minus lambda is invertible. No element in the spectrum can have absolute value strictly less, no element outside the spectrum, I'm sorry, can have value strictly or less or equal than 1 because of this distance, right? I mean, otherwise A and A minus lambda would have distance less than lambda in absolute value, and that would contradict this one. And hence, note also that, and hence this. And these are the two numbers that I want to get into contradiction. The L2 norm will be less than 1, while the spectral radius is 1. How to do that? I have only these two things to compare, right? Note, define R is just the limit of A to the 1, this. And now I define an L2 spectral radius where I replace the operator norm by the 2 norm. I just defined this. I mean, like one can make sure that this is well defined. And this is the number that is called the L2 spectral radius. I will show that the L2 spectral radius is equal to the L2 norm of A if I pick my A in a suitable way. I think I will make it this one like what? Okay, let's do this. I allow myself some approximations. Approximations are swept under the carpet from now on. So A is then suddenly an element inside the group algebra. I can do this up to approximation. And what I can do is, by property, let's give it a number. By this one property, property 1, there's G and G such that the support of I times G inside gamma generates a free subsemi group. Okay. And now, why is this useful? It helps me to calculate A to the n. A to the n will, as a coefficient at a product of GNs, where G1 up to GN are in my support here for I, will be just I G1 and this is a consequence of this property. I mean, you have to calculate the convolution, of course, correctly, but this is the one thing that you're interested in. So you get basically this out. Hence, with a short computation, we will see that the 2 norm now can be is compatible suddenly with powers. I'm sorry. Now I made a mistake. I should have replaced A by I times UG. I'm sorry. Obviously, for A as such, it wouldn't hold. I have to move the support according to that property. The support of my element A times UG will be exactly the set. And that's what I, of course, used. I'm sorry. So this line is obviously important. Okay, but if I have this, I look at these definitions. I can resolve my right-hand side with the 2 norm of A to the n to the 2 norm of A to the n. I take my nth root of that, so this is just the norm of this, and combine this with RD. So this one is this. Well, let me just write it down in the formulas because it holds in complete generality. So this was the definition, right? Now it's a general fact that the 2 norm is bounded by the operator norm. That's always true. So I can always do this. And now RD shows me that this is less or equal than a polynomial f of, let's say, r times n for a certain r times the operator norm of a to the n and this is this. This is sorry. Here, this is r of a, and this one was this, and here. Okay, so what did I do? This step is the crucial step with RD. I simply look at this operator norm, which I cannot in principle really control, and I estimate it by this 2 norm. And the question is, where does my polynomial get evaluated? Well, there is a certain R in which defines the ball in which the support is contained of A. And if I take the nth power of A, what I can say is that the support of that nth power will be contained in the ball of radius n times r. That means I do get a polynomial term here that I do reduce exponentially. This one drops out in the limit, and hence my L2 spectral radius remains. What I have shown here is that the L2 spectral radius is equal to the spectral radius, and that was exactly the contradiction that I had announced. So this is a blueprint for proof. And now all these different results, I mean, this one was a sketch. I mean, this was giving the basic concept and the idea. Here, this one systematized this one, and I guess the blueprint is very close to what they give actually literally as a proof. This was working a lot with the geometry of the asymmetrically hyperbolic groups, where you cannot literally get this criterion 1 that I had put on the other side with this free subsemi group, but only for very specific elements, and you had to work around things quite a bit. And what I did was more operator algebraic that could update such results to this setup. There were certain things that one can do to just update this from an operator algebraic point of view. Okay. I think it's 5 o'clock and it's a good time to stop. Thank you for your attention.
Any questions in the audience?
For your result,
Yeah.
also you use the boundary of the hyperbolic groups to show the property A?
No, I mean, like no, as I said, it's an operator algebraic result. I can tell you what one can do. I mean, one can prove that in general, if stable rank 1 is proven according to this blueprint, then you automatically get it for arbitrary twisted group C star algebras. And there's some theory that reduces this type of statement to the corresponding stable rank 1 statement for certain twisted group C star algebras. And for these ones, you can deduce it from the results that were there the way I just mentioned. So 2 steps. Look at these things. Use I mean, this is green in primitivity, nothing too crazy. You reduce it to twisted group C star algebras by this for a different group. But you observe that your different group is still in this setup. So what you can do is like observe that whatever they do, you can almost black box. I mean, almost black box it really, and deduce that it also implies the same result for the twisted group C star algebras, and then you're already done. It's very quick.
Okay.
Like, I mean, I can explain you but maybe it's a bit too much technicality in front of everybody. But it's not too difficult. Yeah.
Maybe later. Okay,
Yeah.
thank you.
Other audience questions?
Yeah, so, well, I mean, I have some question which looks like very opposite of stable rank one. So it's not completely related to your talk. But do you know an example of a group for which the unitary group of the group system algebra mod, the connected component is not commutative?
No, but I can tell you examples for which I do think it is the case, and I have hesitated now for 3 or 4 years to actually start proving this. The basic example for which you expect this is take just the Heisenberg group. I mean, it will map into the unitaries of, I mean, no reduced necessary, and you can do this one of the same C-star algebra, obviously, and I suspect this is isomorphism, and then it's not abelian in particular. I can tell you the proof strategy even, but I didn't find the time to actually do it. Yeah.
Okay, yeah, thanks.
Questions? I have one. So you mentioned in here you look at the twisted group. C-star algebra.
Yeah.
So is it true that if you have a group C-star algebra who's got stable rank 1, then the twisted group C-star algebra has stable rank 1?
In this generality, I cannot know. I don't know. No, I mean, I really use the fact that stable rank 1 is always proven the same way, basically. So you look at the proof and say, well, I mean, then it also implies the one for the twisted group C-star algebra via a small trick. But it's an interesting question whether, in general, stable rank 1 for group C-star algebra automatically, regardless of the way you prove it, would imply stable rank 1 for all twisted group C-star algebras. Yeah. I mean, I guess the first thing you should do is probably look at this for co-cycles which are connected to the trivial co-cycle in the corresponding topology on H2. That's how I would start, because then you have deformation arguments in principle at hand. And I guess we discussed about how deformations might interact with stable rank 1. So this would be my strategy to prove it. But this was something I at some point figured when I proved this, that it's an interesting question indeed to address, but I didn't spend time on this.
It doesn't hold for twisted groupoids C-star algebra.
Aha, so there in groupoids one has a counterexample?
Yeah.
But this is for set stability. It's not even stable rank 1? Aha, okay, I didn't know that it's not even stable rank 1, that example. Yeah, okay. And the co-cycle, I mean, it's
So
coming from a co-cycle or a twist? I mean, a bundle.
Twist, so I don't know if it's a co-cycle.
Aha, so this might be an actual obstruction. Right. I should look at this example. What I would first suspect is to falsify the statement whether one can apply deformation methods would be to check whether the twist lies in the same connected component as the trivial twist. Then, yeah. But good. I wasn't aware that they had also shown that it's not stable rank 1. That example.
So are there any results for groupoids other than group?
Yeah, often, like, I mean, just for transformation groupoids a priori, right? So there's one other method that proves you stable rank 1. I mean, classification people are often interested in amenable groups, set to the n, and these guys. And there you can sometimes approximate your C-star algebra in a suitable way by subhomogeneous algebras, where you basically follow parts of orbits and then cut, and you get nice enough subhomogeneous C-star algebras. But this gets, like many of these parts of classification, extremely technical. I honestly don't know so much the techniques here. This one?
Clear that it, yeah, I mean, you said this one, group style. Is it clear that you need a non-amenable C-star algebra for this to work?
So, I mean, if you have an amenable group and it has property RD, then it will have automatically polynomial growth.
Right.
But if it contains a free subsemitic group on two generators, at least then it has exponential growth. So the two exclude somehow the only, they exclude each other in the amenable setup. So this setup doesn't work for amenable groups. Yeah.
If we have no further questions, then let's thank Sven again. And I will just quickly advertise next week's talk. Laurent is coming back. We'll talk about continuous fields of interval algebras. See you then.